Good morning, everyone. Welcome to this webinar. Just quickly introducing Katonic. We are here to operationalize AI at scale, and our platform enables data scientists to perform their workflow in a scalable, reproducible manner. And most importantly, it reduces the friction between experimentation and productionization, and this we believe will ultimately drive adoption of AI at a much wider scale than we currently see prevalent in the industry. About myself, my name is Girish Ramji. I'm Chief Strategy Officer at Katonic. I have experience spanning finance, technology, data science, and machine learning. And I'm here today to talk about an interesting use case. Our problem statement for today is how can we measure and visualize the performance of an object detection algorithm on multiple data sets, which possibly come from different sources, the objective being to decide whether the object detection algorithm that we're using, is it the right choice for my use case? So think about a situation, let's imagine a data scientist at an image-based social media platform like Instagram. They're obviously tasked with trying to analyze all the images that are being uploaded by the users, to convert it into an insight on what kind of contextual information is available about the user base based on the objects that are found in the images that they're uploading. So, for example, if I'm playing with my daughter and my pet, then being able to identify that there's an adult in the picture, there's a child in the picture, and a dog or a cat in the picture would be a very helpful contextual information based on which further recommendations might be made to me as a consumer of a platform, of any image-based platform. But oftentimes what happens, right? I mean, of course, if you're Instagram, then you already have an amazing data science platform on which you can evaluate different algorithms. But what if you're a smaller, scrappier startup, or you have access from your user base with to a large number of images, and now you're trying to figure out whether YOLO, whether a specific object detection algorithm is actually going to work well on your data set. So that is the setup over here that we're trying to shine a little bit of light on. So what we're going to do further, we are going to choose a specific object detection model. And what we're going to do is we're going to choose an object detection model called YOLO. And YOLO stands for you only look once. And what that means is that the algorithm builds an end-to-end pipeline that tries to predict directly whether a particular grid inside an image contains an object of a particular class or not. Now, YOLO, when it first came up, it offered a significant improvement over prior methods, which used to take a two-stage approach. Where in the first stage, they would first try to figure out whether a bounding box contains an object or not. And in the second stage, they would try to use a classifier to actually do the classification. Now, that approach had a couple of limitations. The first limitation was that the accuracy has actually got confounded a fair bit because of the two-stage algorithm. And it was quite slow to run because you had the two-stage process. So YOLO actually created an improvement on those benchmarks in terms of accuracy as well. But more importantly, it was a much faster algorithm than the two-stage algorithms. So that's how YOLO gained popularity, and we are using that to illustrate how you would go about evaluating whether YOLO is a good choice for your data set or not. And now if you want to find out more about YOLO, then That's the homepage of YOLO. You can go over there and read about it yourself. If you're curious, there's a lot of insightful information available over there. But let's talk quickly about our data set choice. We're going to use a data set called COCO. COCO stands for Common Objects in Context. And there again, we've shared the website over here. And what I'll do, I'll quickly, let me quickly navigate to the website just so that you guys get a sense of what kind of images we're talking about over here. Right, so that's the COCO website. If you choose, say that's the bird class of COCO set images, and we look for those images, and we can actually see some of the so you can actually see this is what a typical image looks like, where all these colored regions are artifacts where humans have gone and said this particular region contains a bottle, or this particular region contains a bird, and so on and so forth. So that's the data set that we are working with. And I'll just go over a few definitions about what we are talking about when we look at different ways of looking at the data. So we're going to call a true positive as a situation where a ground truth bounding box overlapped with a predicted bounding box. Now, what is a bounding box? So if we go back to these kind of images, so over here in this particular image, for example, you don't, it's not a rectangular shape that captures that bottle over there. It's rather an arbitrary shape that has been drawn around it very precisely. But this actually makes things quite challenging for image detection algorithms. So what we typically do is we draw a rectangle around those things. And when we do that, it starts looking like that. So if you look at an image like that, so you see that blue box, that is a bounding box. And inside that bounding box, we are saying that it's a bed that's located over there. So that's what we mean by bounding box. And coming back to the definitions, we are essentially saying that we are doing a good job of making a prediction when the actual bounding box that contained an object as annotated by a human annotator overlapped with what we said was a bounding box that contained the same object, contained an object. But when we do this overlap, what ends up often happening is that the two rectangles don't overlap with a large enough area. So if the rectangles overlap with a large area, what was actually annotated and what was predicted by us, if they overlap with a large area, then we're doing a good job. But we're not doing a really good job until these rectangles overlapped and the class matched what was originally proposed. So that is the scenario in which we are truly confident that we got a true positive. So going back to our example image over here. So if, for example, I drew a bounding box around there, then it would have a low overlap area with the actual bounding box of the bed. But if I drew a bounding box over there, it would have a much higher overlap area with the bounding box of the bed. So before we can say that we are doing a good job, first of all, we need to make sure that that bound area overlap is high. But then if the area overlap is high and we still end up saying that's not a bed, but it's a chair, then we're still not doing a good job, right? So that's the idea over here. When we say a true positive, we did a big overlap with the bounding box and the class label actually mapped with what the human annotators said. Then we say we got a false negative when both of them overlapped, the bounding boxes overlapped, but the class label didn't match. So we called it a chair or a cat or a dog instead of the bed. And then the third scenario is when we have a false positive. So here there may have been overlap, but the overlap was not sufficient. So that is where we have this threshold over here. If the percentage of area overlapping was less than 0.5, but we still said that there was something in that bounding box. Right, so that is a false positive because we thought there was an object over there, but there was nothing actually predicted. And in the misses, where we looked at all those kind of overlaps, but we were not able to predict any class whatsoever for the entire image. So those are the four scenarios that we're going to use to do the evaluation. And with that, I'll just pause for a couple of minutes before we get into the more hands-on part, where we start looking at how we actually run this on Katonic. Are there any questions about the problem statement or the use case, the way we are setting up about YOLO, about COCO? If there's any questions around those lines, happy to take them now. Just either type them into the chat or put them into the or just raise your hand and we'll see if we can unmute you to the. Okay, so there's one question that's coming. For IOU to work, each image should have one ground truth object and one object prediction. Thanks for the question, Shudong. I hope I'm pronouncing your name properly. So it's what you're saying is correct. Each image should have one ground. Each image does not have to have only one ground truth object. It might have multiple ground truth objects inside it, but each bounding box should have one ground truth object associated with it. And if there are multiple objects, then you might have overlapping ground truth bounding boxes. So that answers the first part of your question. And for object prediction, again, it's the same thing, right? So if we take for example, this particular image, over here, we might have a bounding box over there that wraps up captures the bird, and we'll have another bounding box over here that captures the vegetable, and these two will overlap to a certain extent. But drawing the bounding box like that.
Shirish, wanted to interrupt you. I think you are not sharing if you are talking.
Oh, sorry about that. Yeah. So if you look at the case of the image over there, so we could have a bounding box like that around the bird, and we could have a bounding box like that over the vegetable, and both of them might overlap to a certain extent. But when we do the prediction, let's say we have a bounding box over there, then it's going to overlap a little bit with both the bounding boxes. So we try and account for that using the intersection over union as a way to figure out whether we had a sufficient overlap or not. Oh, thanks, Akshay. Thanks for the feedback. Any other questions before we move into the hands-on part? Sorry, Shudong, did I answer your question? Great. Cool. So let's go into the more hands-on part. Can I check if all of you have access, have already set up accounts to app.katonic.ai? Then you will be able to follow along. So if you haven't signed up for a free account, then please, Siddharth, if you could share the link so people can follow through. Yeah, you can sign up over there. That's going to you just put in your you just sign up over there with your email address, and we'll create a free account for you on our free layer license, and you can follow through with the tutorial from there. Am I still sharing my screen? Yeah. Okay. So when you land on the Katonic platform, you're basically going to be seeing the dashboard over there. So in order to start working through with this example, I request you to go to the App Store. And in the App Store, this particular use case is available under Technology. Yeah, so yeah, so so over here, basically, if you go launch the notebook, it's going to take you to the GitHub repository, which has the notebook. But if you haven't done so already, what you should do in order to bring this into your workspace, you actually, sorry, you first need to create a workspace. I already have a workspace running over here. So I'm going to be connecting to this workspace, but you can use the create workspace widget to create yourself a workspace. And then when you click on connect, you're basically going to be in your Jupyter Lab workspace. Once you're in your Jupyter Lab workspace, you can yeah. Give me a minute. Yeah. Um, okay, I mean, what you should be doing, I mean, you should be able to get a terminal window over here. We'll get back. I am forgetting where exactly the terminal window is right now, but you can use the terminal window to clone the repo into your space. And once you clone it, you'll have a workspace available over here. And in that workspace, you'll be able to find the YOLO notebook. So you just yeah, there you go. You got the YOLO notebook cloned in over there. And we are going to be working with the evaluation. Sorry, give me 1 second. Yeah, we're going to be working with the demo. So we're going to be working with this notebook, which I have open over here. Now, once you have the notebook open, you basically go into the pipelines and you define, if you want, you can define an experiment name. You can give a pipeline name. You can put in a description for it. Now you need to make sure that the storage class name over here is set to rook cepfs. That's just part of the way the Kubernetes pods are set up. The file system that we access needs to be named accordingly. And over here, on using the volume name, you'll need to go into your file manager. And you need to pick up that name, the private storage name, from your file manager to put it in in the volume name. Now, once you have this, you'll be in a position to execute this notebook, which already has various annotations, which let it be run as a pipeline. So you've got the import section where we are importing all the necessary components, libraries. We've got function definitions. These are all the various transformation functions that we're going to be using in the course of the evaluation. So there's a function to compute the IOU, there's a function to compute the overlaps between the bounding boxes, and there's functions to read data files and so on and so forth. So I want to go into detail on those implementations. The next section down here is these are the parameters that we're going to be using for running our pipeline overall. This is just like input parameters for the pipeline, which are going to be invoked by some of the downstream steps. And then you have the various step definitions for the pipeline. So we'll go through at a high level some of these steps in a moment. But these annotations, essentially when you start writing your code, you get the option to go in and give your pipeline step a name, and you're also able to create dependencies saying that what are the steps that need to have executed prior to the execution of this particular step, so that we can go ahead and so that the execution can move on to the next step. So we've got a few different steps over here. Now, when you compile and run this pipeline, what it's going to do is it's going to validate the notebook, compile the notebook. It's going to upload the pipeline so that it starts executing, and it's going to start running the pipeline. So this was the status for my previous run, and this is the status for the current run. So you can actually go in there and yeah. So there you see the pipeline has started executing, and the first step of the pipeline has started running. Now, while that's executing, I'm just going to go to a previously run pipeline. And basically the way you can get over here is you can go to your jobs. You can go to your experiments. And there under the YOLO v3 experiments, all my previous runs of this pipeline are stored over here. So you can see the pipeline that I just started, that is in execution status, but there are two previous runs of this pipeline that have already completed. And as you can see, the pipelines took about 8 minutes to execute each time. So what we're going to do is we're going to look at the pipeline now. So the first step in the pipeline, I mean, of course, after we're marshalling the volumes for our Kubernetes pods, is we are going to read ground truths and predictions that we have generated a priori. Now, what we're not covering in this teach-in is we're not actually showing how to deploy the YOLO model, nor are we showing how to train the YOLO model. What we have done is we have executed inference on using the YOLO model on an annotated data set, which is the COCO data set. And we are loading up the predictions made by the YOLO v3 model as the first step of our pipeline. Once we do that, we are within this part of the pipeline, we are splitting it into 3 data sets. Now, the intention of splitting it into 3 data sets is to simulate a situation where you're actually getting these annotated data sets from 3 different sources, and your motivation is to try and see how the behavior of the YOLO algorithm differs between these 3 scenarios. So once you have those 3 data sets split, the next stage of the pipeline for each of those 3 splits, we are generating confusion matrices, and then those generated confusion matrices go into the evaluation metrics for each data set. And then we bring those evaluation metrics across the 3 data sets into a final evaluation, a final set of performance metrics that compare the 3 of them against each other in a single view. So before I get into each of these in detail, let's just take a look at what's going on with our pipeline execution. So there you see the pipeline execution is proceeding along. That first step is completed, and now we are generating confusion matrices for each of the three data sets. So this is going on in parallel in across three different Kubernetes pods effectively, because each of these annotations that we created in the notebook could potentially be scaled independently. So if, for example, the data set 3 was 5 times as big as data set 2, then this pod might get scaled up, will get auto scaled up a lot more than you might see for data set 1 or data set 2. But the important thing is that the execution of these three steps are going on in concurrently, and we are not, compared to how you would execute in a notebook, you would just go top down one after the other. This gives you the it makes it a lot easier for you to still pursue the same style of programming, but you're still able to make sure that execution happens in an asynchronous manner and brings all the data back into the same space. So if we, okay, let's now go into the evaluation metrics of the already executed pipeline. So let's just take a look over here. So when you click on each of the components, what you can do, you can look at all these different tabs. The input and the output, this is basically tells you what goes into plot evaluation metrics. So we have the IOU threshold as a parameter over there. We've got the volume name, which is a global parameter that goes in for all the pipeline components. And then we are setting some parameters about what is the size of the validation set, and we also need to know what is the private storage identifier. And here we see all the output artifacts, the metadata about the pipeline, the evaluation metrics, and any log lines that you had put into your code. Those will also be available over here. And then when you go into visualizations, any visualizations that are generated by a code can be looked at over here. So let's just zoom in over here. Um, over here, these are some of the logs. So we are using TQDM to track status. When we're calculating the visualizations over the entire data set. So that kind of gives you a progress report. And then here is the first major evaluation artifact. And what you see over here is for all the classes in the COCO data set. So you can see obviously the classes like person, bicycle, car, motorcycle, so on and so forth. We are reporting on the 4 different class definitions that we mentioned. I would say scenario definitions that we mentioned, right? If you remember from the first part of the presentation, we defined what is a true positive, what is a false positive, what is a false negative, and what is a miss. So here you basically are seeing what percentage of the ground truth for a particular class ended up in one of these scenarios when we ran prediction. So this is also a heat map view of what's going on. So obviously you can see over here and this cluster of classes where we have cat, dogs, horses, sheep, cows, elephants, bears. We have a pretty high true positive rate. Um, uh, but if you look over here, and you have cups, forks, knives, spoons, bowls, and things like that, yeah, we're not doing that well over here. So that kind of gives you a good sense that, the YOLO algo works really well for animals or works for animals and maybe for humans as well. Think of human as a social animal. But these kind of small objects, right, typically where it's tougher to identify those bounding boxes, and many of them might be clustered together very close. That's where it's not performing that well. So that's the first way we get some insight into what's going on with our data set. The second way we introspect, we just look at the absolute counts as well, right? And there again, this might give us a sense for, are we getting these kinds of biased, these kind of differences across the classes? Are we seeing that on account of, lack of support for a particular class? So this just helps us answer those kind of questions. And then this is a very interesting one, right? So you remember one of our class scenarios is a miss, right? Where we don't find anything at all. So what we're trying to do over here is we are trying to look at the ratio of how often do we have a miss versus how often do we have a true positive. We're trying to articulate that scenario, and we're looking at that to see what's going on across the different classes. So, so you can see over here for bicycles, for some reason, we find it extremely difficult to even identify a bounding box. But we don't have, we definitely have a relatively lower miss rate for some of the other classes. So this leads us to a question. I mean, why is this really happening? My personal guess, why is it happening? In a bicycle, you have a lot of empty space. So there's a lot of background along with the image itself. And when there's a lot of background, it becomes tougher for YOLO to actually figure out that that there is an object over there, like a solid object without any interleaving background is a lot easier to classify than an object which has, which is a bit stop and start. I mean, in the bicycle, you have the wheel, you've got the spokes going around, and through the spokes, you actually see the background. So YOLO starts thinking that's actually background, and hence it starts classifying the bicycle class as a miss. Where it should be finding a bicycle, it actually doesn't even realize that there's a bounding box over there. So that's quite an interesting metric to have a handle on, the ratio of your misses to your true positive. And this one, this you can think about it as a business metric really for your data set. So for example, if you're, say you've given annotation tasks to 3 different groups of people, and when those annotations came back, you see this kind of a disbalance in your class because there is one class that gets a lot of predictions. So then, you might actually become a little bit suspicious, right? I mean, are toothbrushes really the most frequent thing in the whole universe? I mean, why is that spiking so high over here? Do I need to go and look into the quality of my data source in the first place? Because if it's not really balanced across the classes, or it does not need to be balanced across the classes, but the distribution across the classes needs to make some amount of intuitive sense. So you can get to visualize those kinds of things as well. This same visualization might also feed into business insight that talks about I mean, once you start trusting your model really, you can use this to drive a business insight that says, hey, 70% of people who are active between midnight and 3 a.m. Are watching Netflix with their dog, right? Something like that, because you would see TV and dog having a very high distribution in those data sets. But that you can only get to that situation once you start trusting the performance of your model by looking at the confusion matrix. So I'll move on. You can also look at a few other interesting visualizations over here. So here we are looking at the recall rate by class, setting the IOU at different thresholds. Now, you remember the intersection of over union is basically looking at the ratio of overlapping area between a ground truth box and a prediction box. And 0.4 means 40% of the pixels overlap between the two. And 0.7 means 70% of the pixels overlap between the two over the area of the union of the two bounding boxes. So here we're just trying to get a sense of what happens if we change our acceptance criteria. If we say, don't be very lenient, right? If your model gets it right 40% of the time, we'll call it a success, and then we'll start seeing whether it got the classes right. Versus what happens if you're very stringent and we say you need to have at least 70% overlap before I'll even consider whether you got the class right. So these are all, different ways to play around, interact with your model, and introspect with your model to try and unearth what kind of scenarios the model is working well in or not. So over here, this kind of tells you, right, that across all the classes, uh, at around the 0.7 mark, or maybe even a little bit earlier than that, you're getting a very high percentage of recall. Right? So you can, if your business problem is focused on making sure that you capture as many instances as possible, then you might be good. You might you can afford to set a high threshold on IOU. That's what this graph is telling me. But then what happens when we start looking at precision? Things start going a little bit wonky over here, right? If you set the threshold at 0.7, then there are very few classes that have a high precision. And it's pretty much just one class. Well, maybe if you draw that line over there at 0.7, there are very few classes that achieve high precision when you set your threshold at 0.7. So if you're in a setup where you can't afford to sacrifice precision, your business problem is constructed in a manner that precision matters a lot more than recall, then you can't afford to be so quality conscious. You have to make some compromises. You need to set your threshold a little bit lower. And when you set your threshold a little bit lower, I mean, it starts looking pretty bleak over there, right? Even at 0.4, there's very few classes, even at 0.4, which make the cut. So if your business problem is focused on precision rather than recall, then at this point of time you're going to be questioning whether YOLO is a good choice for you or not, right? And then again, you can do the same with the F1 score as well, which at least tries to achieve some amount of balance between precision and recall. But in the real world, often, you do tend to have problems where recall matters a lot as long as you can achieve a certain amount of precision. So F1 score is great to look at, but sometimes you're better off just looking at the trade-off between precision and recall and constraining your precision so that it's not below an acceptable threshold, but after that you just try and maximize your recall. Yeah, and so yeah, that's the framework of how we evaluate the performance on a specific data set. As you can see, you can look at that visualization for each of the three data sets by going into the corresponding pipeline component. So I won't go into each one of those, and you guys can just, once you've got your accounts and workspaces set up, you'll be able to execute this and reproduce this for yourselves. So you can introspect this in detail yourselves. But keep in mind that here we've artificially created three data sets from three different sources. So you're going to be seeing the same kind of patterns over here, right? Again, you're going to see the same classes being performant versus not performant. But if you bring your own data sets, and you can, if in the README for this particular app, you will see instructions on how you can run inference as well using YOLO. So if you follow that and generate your own data set with the predictions, those predictions can be loaded up into this pipeline component, where you just provide your preds.txt as an input file, and then you can use your own data set as well to reproduce this kind of evaluation on YOLO v3. Okay, so moving on to the last component, which is where we are bringing all the three data sets together into one space and trying to see how how YOLO performance looks like compared to each other for the three data sets compared to each other. Here again, if we go into visualizations, let me maximize this again. And here you can, so each of the three bars for a given class tells you how the precision varies across the three data sets. And that's legends. The yellow is set 1, the blue is set 2, and the red is set 3. So there again, you can see one of the things that again makes you feel a little bit uncomfortable over here is how much of a variation there is across data sets for some of these classes, right? I mean, in general, if these things are stacked tightly together, it gives you a little bit more confidence. It tells you that, you know, across data sets, it's the performance doesn't vary a lot. More than the absolute number itself, you know, across different random sources of data, if your performance is fairly invariant, then at least you know that, you know, your precision, even though, let's go to the bottom so it's easier to see the numbers over here. So let's say over here, we are saying that precision for person is tightly is between 0.5 and 0.55 across the three data sets. So it actually gives you a high amount of confidence. The precision is actually 0.55. But if you look at this one, for example, it varies a lot. It's varying between 0.6, 0.57 for this data set, and all the way up to, you know, almost 0.75 for this data set. So there's a very wide spread over here across the three data sets. So that kind of reduces your confidence whether, you know, do I really know what is the true precision when the range of values is so high? So these kind of visualizations force you to ask yourself these kind of questions about whether your model is working for you or not. In general, I tend to prefer situations where we have a tight cluster around the precision and recall values, even if those values are low, because at least then you know that your experimental setup is getting reproduced across different slices of data. But if it is not clustering tightly in a small range, then you don't have confidence in your experiment. And so it's quite important to look at these kinds of things and not just say, hey, I've averaged my recall across all the classes and I'm getting 0.65, so I think I'm good. No, you need to look into these more granular kind of metrics to really understand the scenarios where your model is working or not working, the scenarios where you can trust your model and where you cannot trust your model. And in general, where you cannot trust your model, you should be a lot more sensitive to those than scenarios where you can trust your model, because that is what will come and bite you at some point of time or the other, because users or your business stakeholders will run into those scenarios sooner rather than later. Here again, we are the next visualization, we're looking at the miss rate comparison between different validation data sets. And at least over here, the miss rates are reasonably consistent across the three data sets, with the exception of some of these classes, like the motorcycles, airplanes, and things. That's where we have a little bit of a variation across, but the miss rates are pretty consistent across the classes. So that kind of drives you to a conclusion that at least in terms of where I am unable to find the bounding boxes at all. Along that dimension, the model performs consistently across the three data sets. Um, and this again is more of what I would think of as something that you would use to have a conversation with your business stakeholders, where you're looking at distribution of instance numbers across the three data sets. And typically over here, if you found a significant difference in these distributions, then that might spark some kind of a conversation with the stakeholders about what was the difference between the three data sets that drove that difference in the distribution. You might even be able to use this kind of visualization to plug it into a measurement of KL divergence between the three data sets, where you can plug it in with some prior knowledge you have about what drives the differences between those three data sets, and then you can use it once to estimate KL divergences between your original assumptions and what you actually see in these distributions. And you can also use it to calculate KL divergences between the data sets themselves to answer the question whether they all came from the same distribution space. Yeah, so that brings us to the, well, let me just show one more thing. Uh, yeah. So remember the pipeline that we started at the beginning of the session. There you say it's also completed execution. So you get the freedom to actually run this over as many times as you want. And you can, and if you keep track of what is changing between the runs, then you can actually go back and use this as a way to compare what is happening across runs as well. So you can set up different pipelines with different input parameters, and you can use this to navigate back and forth to compare what is happening across these scenarios. When you change those parameters, what changed? You can use that, and you can repeatedly run the same experiment in different scenarios and have a consistent way to come back and answer the same questions. So that brings us to the end of the hands-on section. I do hope some of you were able to follow through. If you had any issues with setting up your account or cloning the notebook or executing the app as we demonstrated, then please feel free to write into us, or I mean, if you faced any issues, you can just put your hand up right now and ask us any questions. I'll just leave the floor open for questions if there are any. Feel free to either put your hand up or type it into the chat. We've got 5 more minutes in case there are any questions.
Girish, there was one question from Deepak. He said that he missed how these data sets were split.
Okay. Thanks, Anuja. So Deepak, basically we used the COCO data set, and let me just so the logic for how the data set is split, that is contained within the first pipeline component. Over here, if I'm not wrong. Sorry, it's so the first pipeline component, which loads the ground truth and predictions, that just loads the entire COCO data set. And you remember that we have parameters over here. sorry, if we go to the pipeline, I think it'll be easier to show it over there. Um, if you look at the input and the output, so we set a valuation set size parameter over here in this component. So that actually splits it into three sets of 5,000 images each from the COCO data set. And that actually is one of the small differences in implementation between these three pipeline components, because here we're choosing the first 5,000, here we're choosing the next 5,000, here we're choosing the next 5,000. So it's a very simplistic split right now, because we're just simulating the idea that your data set could come from three different sources. But if you really had data from three different sources, maybe you would have three components here for loading those three data sets and feeding those into the confusion matrix code. With that, I hope that answered your question, Deepak. Yeah, it's effectively a random sample. Well, to get a random sample, we would need to randomize it and then do the subsetting. But you can think about it as a random sample pretty much. Just keep in mind this is for illustration purposes, right? I mean, that's why using the COCO data set and doing this. What would be a lot more interesting is if you could take the COCO data set and you could take the OID data set and you could take 3 or 4 other public data sets, or if you have a private data set which is annotated and then you run it against that, then you can use the same app to do the evaluation as long as you've prepared the data in the same way. So I think there's a question from Shurong. What is behind the pipeline function, pure Python script, or are some other ETL framework supported? That's a great question, Shurong. The pipeline, so we are basically, it's inspired by Kubeflow, the way we are doing the pipeline. So you still implement pure Python code, but when you tag your cells in your notebook with those annotations that we showed you over here, those annotations, those actually are used to transform. Like for example, when we used that annotation for the pipeline step, those 3 cells got injected into a Docker container, which got executed as a pipeline component over here. And each pipeline component, essentially, when you have the input and output, right? It's creating sourcing its input artifacts from the volume and the private storage, and it's dumping its output artifacts into a predefined location from where the downstream components can pick it up. In terms of whether other ETL frameworks are supported, not in the free version, but in our Teams version and in our enterprise version, we have the ability to implement bespoke connectors with a large range of data sources. And if there is a requirement to bring in a specific ETL framework, for example, if you want to use say Airflow, we could definitely look into figuring out a deployment mechanism so that you can bring your existing Airflow scripts and run it on our platform. Are there any more questions? Great. If not, then sorry.
Yeah, Girish, I would like to take this moment for thank you so much for this wonderful and very informative session it was. And I'm sure everybody here would agree on this. And thank you so much, attendees. do sign in. Siddharth has already posted the link, and give your valuable feedback so that it will help us to improve. And yeah, that's all.
Great, thanks, Anuja. Yeah, please, a feedback loop is the most important thing for a machine learning algorithm or a growing business or a growing startup. So please help us out with your feedback. It'll help us iteratively improve the quality of these sessions and improve the quality of our product as well. So our community is our biggest source of support. So do give us that feedback. It's invaluable to us. Thank you so much, everyone.